Welcome to e-Padasala lecture series in computer science. In the last module, we discussed about the analysis of iterative algorithms. In this module, we are going to continue the discussion about the analysis of algorithms. So, in this module, we are going to discuss about different scenarios like best case, first case and average case scenario of algorithm analysis. Then we are going to discuss about the important concept of rate of growth. Using this concept, we are going to compare various algorithms that are suitable for given problem. After that, we are going to discuss about the asymptotic analysis, and finally, we are going to conclude about various asymptotic notations that are available. Using these notations, we are going to convey the complexity of the algorithm analysis to the programmer, so that he can have an idea about the efficiency of an algorithms. So, today we will start our discussion about the various case analysis. Last module we discussed about how to compute T of n in terms of steps or counts. It is irrational to put all the analysis based on just T of n alone. So, today we are going to discuss about the various analysis, where we are going to discuss about different case scenario. Just I am recollecting what we were discussing in the last module. So, there are 4 steps. The first step is we have to measure the input size, and in the second step we have seen how to compute T of n based on the step count or operations. So, today we are going to discuss about the third step, that is we are going to construct different case scenarios, and we are going to discuss how to formulate the T of n. And finally, we are going to discuss about the important concept of rate of growth. So, let me recollect what exactly the input size is all about. So, last module we have seen that the input size is very important, because algorithms that have larger instances require more resources to process correctly. So, I was giving a small example that sorting of 10 numbers is an easy task. On the other hand, sorting of 1,000,000 numbers is going to be a very difficult task indeed. Therefore, the complexity of the algorithm depends more on the input instances. So, using this concept only, we have predicted the run time as the size of problem. So, you can recollect the run time of an algorithm is defined as the function of the input size. Suppose if the input size is small or capital N, then the complexity of the algorithm is going to be measured as T of n. Fine. So, once you find T of n, we can say what the complexity of the algorithm is all about, but it is irrational to put all the onus on T of n to communicate the complexity of the algorithms. So, we have to construct the various scenarios, and we have to explain what T of n for a particular algorithm. So, first we will talk about the worst case runtime. The worst case runtime is defined as the maximum number of steps or operations that are required to solve a problem of instance size n. So, in other words, the worst case runtime is going to tell us how maximum operations or steps that are required to solve a given problem. The next scenario is called the best case running time. So, the best case runtime is going to be defined as the minimum number of steps or operations that are taken by the algorithm to solve a problem of instance size n. So, these will give you some sort of an idea about various bounds. For example, the worst case analysis gives the upper bound on the running time. What does it mean? It means that the upper bound gives a guarantee that the algorithm would not run longer no matter whatever the inputs are. In other words, this is the worst case scenario of the given algorithm. I can give you a layman example. Suppose if somebody asks me the airfare of the flight from Chennai to Delhi, I may not know the exact airfare, but I can say fine, I do not know, but it will not go beyond, let us say, x amount. In other words, x amount is going to be the upper bound. So, beyond which the airfare will not be there. So, this sort of upper bound is what given by the worst case analysis. The best case analysis gives the lower bound. That means, it gives the time. So, where the algorithm is going to be the fastest. The lower bound is always computed for the problem and not algorithms. In other words, given a problem, if there are n ways of solving that, the best way of solving is going to be the lower bound of the given algorithms. So, in other words, we can summarize these things like this. The types of analysis can be a best case or worst case. In the best case, we can get the fastest the algorithm that can run we can get, and in worst case we can get the longest time an algorithm can take for the given problem we can find. In other words, this is what the scenario is going to be. Suppose if I get the algorithm and if I have some sort of the resource cost measurement, then the worst case gives you the upper bound and best case gives the lower bound, and we can say that the average case is something like where we can get in between the worst and best case scenario. Fine. We will take one simple example of how to apply these concepts. So, let me take the simple problem of linear search. You all know what the linear search problem is all about. Here we are given an array. The array consists of n elements. The elements can be an integer or any other element. So, let us assume that the elements are numbers, and the linear search problem is that given a target, we have to see whether the element is present in the given array or not. Fine. This is how the algorithm goes for this particular problem. So, you can see algorithm, then I am giving a name for the algorithm called search, then it takes an array A. Array consists of n elements and you have a target. So, I am starting a loop here. So, under these conditions, if my target is not there, then I am going to increment the index, and let us say if a of a index is going to be the target, then I am going to return the index, otherwise I am going to return -1. Fine. So, in this case, let us assume that the target record is either present as the part of the array, or it need not have to be present in that array at all. In that case, what would be the worst case time? The worst case time for this problem is going to be what you say, either the target is going to be the last item of the array. So, in that case n array accesses are required, or in the worst case what we are searching for may not be present in the array itself. Again in that case, at least n comparisons are required to declare that the target is not present in the given array. So, in short, in worst case at least n comparisons are required to find out the element if it is present and or it is not present as part of the array. Fine. What is the best case for that? The best case for this is what we are searching for is present in the first place of the array itself. In that case, using one comparisons we can find the element, the target element that we are searching for. Fine. Then what is average case analysis? Average case analysis is the most difficult part of any algorithm analysis, where we are going to say on the average how many comparisons are required to find the target. So, we require normally the probabilistic analysis for that. So, we are making an assumption that what we are searching for may be present in any part of the array. Therefore, the probability is going to be the equally likely, and what we are searching for is present in the array. If that is the case, fine, we can take a small example. If we assume that the given array consists of 10 records, then suppose if the target record is present in the first place, then we require one array access. If it is the second record, then we can say that it requires 2 array access. If it is the third element, then 3 array access are required. In short, we can say that the average of all these searches is going to be 1 plus 2 plus 3 up to 10 divided by 10. So, we can see that it is going to be 5.5. So, in other words, 5.5 is the average number of comparisons that are required to find the given target. So, we can summarize everything like this. So, in best case, using one comparison we can find, in other words, T of n is going to be a constant, and in average case at least n by 2 plus 1 comparisons are required, and in worst case, so n or n plus 1 comparisons are required for that. Fine. In other words, the best case, worst case, average case gives the various scenarios of how T of n can be. Then once we have this analysis, then we can start comparing the algorithms. For example, let us assume that we are given two algorithms A and B for solving a problem. Let us assume that the first algorithm takes 50 n square, that is T of n is going to be 50 n square, and for algorithm B let it be n. If this is the case, find which algorithm I should take. In other words, if a problem like this is given, fine, I can take an arbitrary value of n and I can substitute into these expressions. For example, if I take n equal to 10, then we can see that algorithm A requires 50 into what you say 10 square. So, that means we can say that 5000 steps are required, but whereas for algorithm B only 10 steps are required. In other words, the algorithm B is going to be better than algorithm A. In other words, we can use the concept of rate of growth as a measure for comparing functions. So, we can take the value of n starting from 1 and we can take that up to infinity, and we can say which or how the functions grow. For example, if we start substituting various values for those algorithms, then the table is going to look like. So, you can see very well as n varies, that is shown in this particular column, then we can see the number of steps or comparisons is going to be for algorithm A is listed here, in B listed here. So, we can say that as n increases, we can see the algorithm A steps gradually increase in large way compared to algorithm B. Therefore, we can come to a conclusion that algorithm B is more effective compared to algorithm A. So, in other words, the rate of growth is the very important concept in understanding the behavior of the algorithms. In other words, it is the core on which the algorithms analysis can be based. Once we have the rate of growth, then we can go for the concept of asymptotic analysis. What is asymptotic analysis? It is not always necessary to find T of n in full manner. In other words, we need not have to compute all the terms. For example, the function of T of n may be having lot of terms like this. So, exact computation of this function is not necessary. Therefore, we are going for the concept of approximation. The approximation in Greek is asymptotic. So, in asymptotic analysis, what we are trying to do is we are trying to approximate this function and we are going to base our analysis based on that. So, in asymptotic analysis, we can ignore the constants. For example, if T of n is going to be a big function like this, then we can ignore all these constants, because these constants are not going to matter. For example, if algorithm takes 2000 seconds and algorithm C takes 2001 second, that one extra second is not going to matter at all. In other words, what is important is the rate of growth and not the exact constants. So, we can ignore these constants so that the expression can be simplified like this. Similarly, we can ignore all other terms and we can approximate this function to the largest degree of the polynomial. So, if this is the case, then we can approximate this to n square, so that the complexity can be expressed in terms of n square itself. Fine. So, once we have the complex function, then we can say all the functions we can group into classes. So, what this concept is that, fine, if an algorithm is having the rate of growth as n square, then we can put all the algorithm that have the same growth functions into one complexity class. Fine. Suppose if we have the classes, then the comparisons becomes easier. For example, if I have algorithm A, which is having the rate of growth as n square, and another algorithm B having the rate of growth as n, then we can easily compare and we can say which algorithm is the best algorithm. So, in asymptotic analysis, all the growth can be grouped into these three ways. One is we can say two functions f of n and g of n grow at the same rate, and one function is growing faster than the another functions, and one function grows in a slower manner compared to another functions. So, once we have this sort of growth, then we can use notations to illustrate how these complexities can be represented. This is what we are calling as asymptotic notations. There are 5 important asymptotic notations we have. One is big O notations, which is used to give the upper bound of the algorithms. Already we have seen how the upper bound is very important in illustrating the complexity of the algorithms. So, we will be using big O notation to express the upper bound. Similarly, the omega notation is used to represent the lower bound, and the average case is going to be represented by the theta notations. Apart from that, we will also use little o notations and little omega notations to express the complexity of all these algorithms. So, we will discuss this one by one. first we will take the upper bound and we will see how this is represented by the big O notations. So, this is the formal definitions. So, we can say f of n is in order of g of n if order of growth of f of n is going to be lesser than or equal to order of growth of g of n within a constant multiple. In other words, we can say f of n is going to be lesser than or equal to c into g of n for every n is greater than n naught, where n naught is going to be a non-negative integer. Suppose if we could able to prove that, then we can say that it is going to be represented as big O notations. Fine. We will take one simple example to illustrate that. For example, I am given a algorithm. So, if I find t of n of the algorithm, let us say it turns out to be 20 n square, and I want to represent this as a complexity function. So, naturally I assume that that complexity function is going to be n square. Now, the question is, can I say this algorithm as order of n square? So, according to our particular formula, so big O notation is possible if I could able to prove that this 20 n square is lesser than or equal to some constant multiplied by g of n. So, here g of n is going to be n square. So, now if I could find a scenario where this condition holds good, then I can use the big O notations. So, now I can say for c greater than 20, we can say that this condition holds good. Therefore, when n is greater than or equal to n naught is 1, then when c is greater than 20, then this condition holds good. Therefore, I can say that this is going to be the order of n squares. In other words, if I could able to find the suitable evidences, then I can say that this is going to be the order of n square. Similarly, you can apply the analysis for these algorithms, and you can say that this is going to be the order of n, the largest degree of the polynomial. This is going to be order of n square, this is order of n cube, this is also going to be order of n cube, this is going to be big O of 1, because this is going to be a constant. Fine. Now, I can extend this definition for other notations as well. This is going to be the omega notations. Now, you can see very well this is the inverse of your big O notation, where you can say that f of n is going to be greater than or equal to c into g of n. So, this is what I said, the inverse of big O is omega, that is if f of n is going to be big O of g of n, then we can say that g of n is going to be omega of f of n. In other words, we can say that f of n grows faster or with the same rate as g of n. Fine. So, you can take this particular example. For example, 6 n square, can I say this is omega of n square? Fine. So, according to the definition, I can say this as omega of n square if this condition holds good, that is f of n is going to be greater than or equal to c into g of n. G of n is going to be n square, 6 n square is greater than or equal to c into n square. So, if I could able to find one evidence of this condition holds good, then we can say that it is omega. So, you can say when c equal to 6, then we can say that this 6 n square is equal to 6 of n square. Therefore, we can say that this condition holds good. Therefore, we can say that 6 n square is going to be omega of n squares. So, in this way we can start proving all the things. The next notation is the theta notation. So, theta notation is the average case. So, where we have seen in the graph, the average case is bounded by an upper bound and a lower bound. So, in other words, if we could able to say that f of n is big O of g of n as well as omega of g of n, then we can say theta is the appropriate notation for those sort of expressions. We can start proving all the things using the concept of limits also. So, using the limits we can prove the complexity of these notations. For example, if we have functions f of n and g of n, then we can say that if the limit n tends to infinity, f of n by g of n is going to be 0, then we can say that this is going to be big O of g of n. If it is going to be a constant which is going to be greater than 0, then we can say that f of n is going to be the theta of g of n, and if it is going to be infinity, then we can say that f of n is going to be what you say the omega of g of n. So, we can take a simple example and we can say for example, if I have two algorithms whose complexities are n and n plus 1 by 2, fine, I can apply the limits. So, if I apply the limits, limit n tends to infinity of n by n plus 1 by 2 is going to be a constant. So, as per the definition, if the limits of two functions turns out to be a constant, then we can use theta. Therefore, I can represent this algorithm as theta of n. We can use little o notation also. So, in that case, we are arguing that f of n grows slower than g of n, or we can say g of n grows faster than f of n. In that case, we can say that f of n is going to be small o of g of n. So, you can say very well this is very much related to big O notation, in the sense that the c is going to be very small constant. Similarly, we can say the little omega notations, where we can say that f of n grows faster than g of n, or g of n grows slower than f of n. In other words, the limit is going to be infinity. Fine. So, in algorithm we will encounter lots of complexity classes like this: constant, logarithmic, log squared, linear, quadratic, cubic, exponential and factorial algorithms. So, in summary, I can conclude things like this: the worst case, best case and average case is very much required to express t of n in an apt manner, and the rate of growth is very important to compare various algorithms, and t of n expression can be simplified. So, approximation can be made use of, it is called the asymptotic analysis, and once the asymptotic analysis is over, then we have to express that suitably using notations that are called the asymptotic notations. So, with this module concludes. In the next module, we are going to discuss about how this concept of analysis can be extended for recursive algorithms. Thank you very much.